I would like to give you now one more example of a function, but with a twist. In the previous examples, we saw how to specify a function by giving explicitly the order pairs in the set. This time, we are going to see how to describe a function implicitly. Let's recall first the two major steps into constructing a relation. We start always with some set x and some set y, then you Cartesian product these two sets, which gives all the pairs of the form x and y. I'm going to represent now this set by the following picture. This circle, where each point in this circle corresponds to an order pair. This is essentially just a step A that we saw previously. Step B, I chose from this entire set of points my favorite points, my favorite order pairs. And those constitute some small subset of the Cartesian product. And as a result, they are considered a relation. Okay? Note that if I choose carefully what pairs go into this subset, and by carefully I mean for each entry x there is a unique y, then this is more than a relation, it's also a function. Okay? This is previous examples. What I'm going to do now is that instead of choosing my favorite elements from the Cartesian product, I'm going instead to choose some rule or characteristic that I want to see common to those pairs in the subset. Okay? Of course, depending upon this rule, this set may or not be a function. And so, let's see an example. Assume that x is a set 1, 2, 3, and 4. Y is also the set 1, 3, and 4. That means that this big circle, each point, corresponds to an order pair where the first entry x ranges from 1 to 4, and the second entry y also from 1 to 4. For the rule, let's specify something simple, y equals x squared. It has two variables, which must be specified by us. Our goal is to choose pairs where the first entry and the second entry satisfy this rule. For example, 1, 1 is an order pair living in the Cartesian product. But does it satisfy that rule? It satisfies, let's see, x is 1, so x squared is 1, y is 1, so you get 1 equals 1. That is a true statement. And as a result, this order pair lives in the subset. Okay? Let's choose now 1, 2 also from the Cartesian product. And let's check. 1 squared, the first entry squared, equals 2. The second entry is y. It is a false statement, right? 2 is not equal to 1. And so, this pair is not in the Boole circle, in the Boole subset, but is instead living in the Cartesian product. Okay? So it's outside. There are many more elements to test, but I'm going to give you the last one that is going to work, which is 2 and 4. You can see it easily because 2 squared is equal to 4. And so, this set also, this pair also lives in the subset, okay? So essentially, the truth set of this thing contains just the points 1, 1 and the points 2 and 4. Okay? Question. Is it a function? Well, look at it. The first entries, 1 and 2, only appear one time. And so, this is indeed a function. Okay? What's the domain? 1 and 2. What's the range? 1 and 4. Okay? This thing is quite easy to see because we have a small set. But let's now try to describe this implicitly. Okay? Let's describe it implicitly. Implicitly, you do it as follows. You say that you want the pairs x and y living in the Cartesian product of 1, 2, 3, and 4 with 1, 2, 3, and 4. So we want pairs living in this arena, but you don't want just any pair, you want those such that y equals x squared. Okay? This single line written in mathematical language describes this schematic. Okay? It tells you what you have to do. What you have to do to reconstruct this thing explicitly. Okay? This time, writing this thing explicitly is quite easy. But as you shall see in a minute, when the sets are larger, this is no longer the case. Okay? So, this is the idea that bar means such that this thing is true. So essentially what you see here is the truth set. This is the truth set of the statement y equals x squared. Okay? The rule that specifies the thing. Okay? Let's now make a small modification, and instead of a small set, let's make it bigger set. So it's R, and now here you have, instead of this Cartesian product, let's make it R times R, or should I say R squared. Note that now x lives in R, y lives in R, so there is an infinite number of elements to test. Okay? In fact, this set has an infinite number of elements. Let's just give some examples. 1, 1 is there, 2, 4 is there. This is fine. But now 3, 9 is there, because 3 squared equals 9. For example, square root of 2 and 2 is in there, and so on. So there is an infinite list of elements. And so it's useful to describe the set like this. Okay? Now, question. Is it a function this time? When you make this modification, is it a function? Well, let's see. To be a function, each first entry must have a unique second entry. But you can see that, well, x lives on R, so you can choose any R. You have to pair it with y, but what you are going to pair it, the x with, must make this thing true. So you choose any x, you compute x squared. X squared is a real number. Is there a y, a unique real number y, that is equal to that x squared number that you chose? So let me put it this way. You choose x, you compute x squared. Now, it's my task to find a y to match your x squared. Well, I'm always going to find that y. Why? Because y lives in R. So you have all the possibilities in R. Okay? So indeed, this is the case. This is a function because there is always a y to pair with x. Okay? What's the domain? What is it a domain? What is the domain of this function? Let's call it this f. This is f. The domain of f. Okay. The domain of f is all the x's. Okay? And you can see it's R. Okay? In this case, this is R. What about the range of f? The range is trickier, right? It's all the y's that you would find in this set. But you see, y is always equal to x squared. But x squared is either positive or 0. And so, the y must be any real number, positive or 0.